Hello and welcome everybody. This is again the MATLAB and Simulink Racing Lounge, and in today's episode we are going to talk about optimization. For optimization, I'm really glad to have Sarah on board. Hi, thanks for joining. Just for guys watching, could you introduce yourself briefly?
Yes, sure. So I'm in the consulting group here at MathWorks. I have a PhD in mathematics, in optimization.
Well, that should help.
I hope I can help you with that.
Perfect. Well, thanks for joining. Why are we doing these episodes? What I see that race car development is all about optimizing. It's not strictly using optimization in the sense of mathematics, but you're trying to improve things.
Sure.
Well, your take on that is?
Yeah, I mean, optimization is a field of mathematics, as I just described, and it's inherent in MathWorks tools already. Sometimes you probably just don't see it, but for example, in PID controller tuning, it's a part of that, and in Simulink Design Optimization as well.
Yeah, well, we have focused on these aspects already. We haven't really talked about the optimization behind. And this is exactly the reason why we are doing that episode. We are going to try to understand the methodology and look a bit behind the curtain of the mathematics.
Yeah, and then hope that you can solve optimization problems a little bit better on your own.
Yeah, that's the goal. Great. Well, today's agenda is basically, we will set up an optimization task from an engineer's point of view. We are going to use a suspension model, a sim mechanics suspension model for that, and that is part of the online training. So you have access to all files. You can do exactly the same that we do here on your computer. As said, we will look behind the curtain, talk about the mathematics, define the problem properly. And then we will see 2 hands-on demos. As said, all files are available. You can do them exactly as they are on your computer. And I think this means jumping into the optimization problem. Your question may be, what's that? Well, that's a cross-sectional view of a suspension. That's part of our online training. And basically, what as an engineer we want to do is we have certain design variables. So guys from suspension team and vehicle dynamics team told us, well, we want to improve the suspension, but you are not allowed to change everything. You're just allowed to change the upper arm length, here specified as X, and the distance between the chassis attachment point measured from the center of mass of that simplified chassis body.
All right. And what do you want to achieve in terms of optimization? So what would be your goal?
Yeah, the goal is to bound the roll center.
Okay, so what's a roll center?
Right. I prepared this slide exactly to explain it briefly. The roll center is defined by the instant centers. So instant centers is nothing but take the A-arms of one side, do lines on them and find the cross-section of these lines. Do that for both sides.
Okay.
Then you have the 2 instantaneous centers or instant centers. And then if you connect them to the points where the wheel touches the ground, as we do here, and again, you take the intersection of that, you have the roll center.
Okay.
This is basically what we want to optimize. And to be more precise, the design goal is we want to have the roll centers 45 millimeters from the ground level, from the street level.
Okay, so it should not exceed that height.
Exactly, it should be below that because it's very important from the vehicle dynamics aspect.
Okay.
That's let's say a vehicle dynamics goal.
Understood. Okay, so let's try to formulate that sentence. The roll center height should not exceed that height.
Yeah.
During the simulation of the system, actually, in a kind of a more abstract kind of way. So this means that we would introduce this height of the roll center to view this as a function h that depends on our design variables, so on x and y.
Sure. Yeah.
And we are interested in the distance of this height to this 45 millimeters. So we could then say, okay, let's just minimize that difference. But what would that do? So that would actually be, exactly the same as if we would just minimize the roll center, right?
It could be also 0 or even below the street level.
Exactly. So this means that we would have a point that is rather as much below as possible, but not just below the constraint of 45 millimeters. So how can we see that? Because this expression here, so this distance is actually positive whenever the bound that we want to achieve is violated, and it's negative whenever the bound is respected.
Yeah, that's why it's just minimizing, it's nothing else.
Okay. Yeah. So, it forces the roll center to be as low as possible. That's not what we want
Not
here.
actually what we want, right.
So we have to extend this formulation. How can we do that? We will introduce a maximum into that.
Okay.
Because I will only want to consider that whenever it's positive.
Okay.
So by taking the maximum from that expression and 0 means I would neglect everything that is negative.
Oh, so how I read the term within the brackets is I maximize either the first thing or I take 0. Or how can I read that?
Yeah. So this means that the distance, this is then now the distance how much the roll center exceeds this height, because it will be positive if the bound is violated, then it will be that value. Yeah. And otherwise it would be 0.
Okay, so our roll center does not go below 45 millimeters.
Yeah, and if it does, we would not have rather a point that is much below it.
Yeah.
So we only care that it's below it and not how much.
Okay, perfect. That's what we want here.
Yeah.
And we picked that example or we picked that optimization goal exemplarily. So whatever your design goal is, specify it like that. This is just a random assumption here.
So now we have like kind of an abstract formulation. So this h here we describe as a function because it's depending on our design variables, but it actually is only a signal in our simulation.
Got it.
So, and now, yeah, this formulation should only force the roll center height to respect the bound.
Yep, and not to minimize it. Yep.
Yeah. This is the mathematical description, so it's one way to formulate that. In fact, since this h is not an analytical function, but is the signal in the simulation, we are only interested in certain times of the simulation, between 5 and 55 seconds. Why is that?
Well, in that case, the simulation starts with an initialization, and there we are not interested in the roll center height.
Okay.
It's not part of what is actually happening, so we restrict it to that time frame here.
Okay. Great.
Just you mentioned two models to describe it. Well, I completely understood that. That's the model 1 is what you just introduced. Why do you need another model? So why do I have to reformulate the problem?
You don't necessarily have to.
Okay.
And you would not necessarily do that on your own anyway. But it's just another possibility because optimization methods that are all behind it,
Yeah.
and we will refer to them later,
Okay.
are really interested in how the thing is formulated.
Okay.
So in this model, we only will have one objective function, which is the output of the simulation.
Right.
And what else do we have? So we could not only give this objective function, but we should also account for additional constraints that we have on our design decisions.
Yeah.
So for example, here you said that, of course, the length could not be negative. Yeah, you might think this is clear, but it's not clear to the solver. So you should at least tell him.
I get the point. So theoretically, while the length or the dimensions can be between minus and plus infinity, but it would confuse the solver.
Sure.
Or would make life a lot harder. And while giving that preliminary information, that's fine, because we know that the arm is not negative length, and we know that it's not longer than 1 meter here, 100 centimeters.
Yeah.
So in case we know it, we should give it to the solver, right?
Exactly.
Okay.
And what we call this kind of constraints are really the simplest constraints, the lower and upper bounds on the variable values.
Got it.
Yeah. And if you have them, please just add them.
Okay.
So as we just mentioned, we can also have a different formulation for that kind of thing, which would model the same situation, but in a different mathematical or abstract way.
Okay.
So how could we do that? We would do that by introducing an additional variable that is not really a design variable, but we only would need that for the purpose of modeling.
Okay.
So we will call this variable m here. And what we want to do is we would just want to substitute this maximum inside of the objective function.
Okay.
So we will have m to be greater or equal to this distance. And now, as same as before, we would only be interested in m whenever it is not negative. Yeah?
Okay.
Because whenever it's positive, this would mean a violation of our bound.
Got it. Okay.
I would therefore minimize this m, which is the violation of our bound.
So in that case, for the model 1, we needed a minimum and a maximum. Here, one minimum is just enough.
Yeah, by
Okay.
introducing this additional variable. This is now a constraint.
Yeah, okay.
And I will have the initial lower and upper bounds that I had before. And in addition, of course, I have to restrict m to be not negative.
Yeah.
Because otherwise, I would not have this
Got it. Yeah,
only
yeah.
positive values. Yeah. So it's just a trick for a different formulation, and a solver might care about how something is formulated or not.
Okay.
So therefore, it's important to just keep
Yeah.
that in the back of your mind.
No, that's perfect. And we will see soon an example where we use different solvers and actually see the difference in the results.
Yeah.
Okay.
Let's have one look before we go on with these methods, right, to have a look at how is a general statement of an optimization problem, because you might come across that when reading more documentation or books on that. So we always have something called an objective function that we already have seen. Then we always have things that we can decide. So we call them decision variables. And in this case, these are the design variables.
Yeah, I had to ask Sarah that question because I read a lot about decision variables, design variables. Some guys even call it optimization variables. It's all the same.
Exactly.
Yeah. No idea why mathematicians are confusing that, but it's all the same. We are talking about, well, the thing we are interested to optimize.
Exactly.
Yeah.
The objective function is typically a linear or nonlinear function. In our case, it's actually a signal in a simulation. So the function is really like a black box function. Then we would have constraints. So we already have seen lower and upper bounds on the variables. And then we distinguish two different types of constraints. The ones are the linear constraints.
Yep.
They are basically matrix inequalities, so equalities. And there could be nonlinear constraints. These are also nonlinear functions that are described as inequalities or equalities.
Okay. So what do we have in our model?
In the model 2, we will have these nonlinear constraints because of this auxiliary variable.
Okay.
In the model 1, we would only have an objective function.
Got it.
And always we have this lower and upper bounds.
Okay. So, and our objective function, is it linear, nonlinear? What is it?
In the model 2, it's actually linear because we only have the variable m.
Okay.
But in the first model, it's nonlinear because we have the maximum of the roll center height minus the 45 and the 0.
Okay, got it.
Why is this important? Because different methods deal with these kind of problems differently, and actually you classify what kind of functions are here involved, and then choose the method accordingly if you have that possibility.
Right. So what I suggest, let's move to a software demo just to see what this can mean.
Yeah. Okay. Why are we even interested in this kind of classifications? Because different situations or different functions actually require different measures, meaning different optimization methods. So here's an example of a function where this is kind of obvious. So why could this be a challenging problem?
Well, even for me as a mechanical engineer, this is somehow obvious. This function has a lot of local maxima and minima, and it looks like, let's do it a bit bigger, it looks like it also has a global one. And well, I think what you are going to show us is that different techniques or different methods will lead to different results, right?
Exactly. So you always start at some kind of starting points usually. So first we will use a mathematical optimization method to solve that using numerical techniques. It's called fmincon, and you can see what just happens. So here this is the counter plot of the function that you can see from the above. Yep. This would have been the starting value, and the black points would be the iterations. And you can see here that it landed in a local minima, which is quite fine, but it's not optimal because the optimal point would be here, the 0, 0. The output on the command line actually tells us that a local minimum was found. That's all about right. And you can see here also in the display the different iterations that you can see in the picture. So another option would be to use like a global method. One would be, for example, a method called pattern search. And how does that look like if we apply that? It also uses iterations, but it's not relying on gradients. So it has more like a search-based technique to choose the next iteration point. And in this case, we are glad because it finds here really the global optimum. We can see here that it took a little bit longer. It took more iterations to solve that because it doesn't have the descent information from the gradients. But you see, different methods really give different results. So depending on the problem at hand, you might try different methods.
Well, and for me now it's obvious if I don't know what methods I'm using, I may end up with a result. I believe it's optimal, but it's obviously not. For me, it's tricky to distinguish between all the methods. What is available and how can I find the right one? This is an important question to me.
Yeah, so we will come to this a little bit later. As I said, there's global methods that can deal with these kind of problems better. And there's this local methods that can really deal better with problems that are kind of well formulated and convex, for example, so that have certain mathematical capabilities that you cannot really test for simulation models. So you can just start with a numerical methods and see how it works and then try different ones. So here you can really choose these different methods that we've just seen in the demo, also in Simulink Design Optimization.
Okay, what might be confusing for some guys watching the video, we have the MATLAB environment. So I have seen a function called fmincon. We have seen pattern search. That means these are the MATLAB functions that are part of certain toolboxes. Optimization toolbox, global optimization toolbox. And then when we go to Simulink, the stuff is a bit different, but under the hood it's the same, right?
Exactly. It's using the MATLAB functions, as you already explained. It's just called a little bit different to give like a more intuitive understanding, I guess.
Okay, got it.
So here you see a window that displays the options if you do a Simulink Design Optimization that you will see in the second demo.
Yeah, we will do a demo on that. We will actually do that, but it's very helpful to see what this actually is. And also when having a look at the documentation. So we will give you a lot of links about all these functions in the video description. So I think this slide is pretty helpful to relate one thing to another.
Yeah. So here you can see that in Simulink Design Optimization, you can choose between 3 different methods called gradient descent, pattern search, and simplex search. And what that really is the gradient descent refers to the MATLAB function fmincon. This is actually solving the second model that we built up. Remember, the one with the nonlinear constraint.
Yeah.
And this was like also the first method we would just see in the demo. Then pattern search is a global optimization method from the global optimization toolbox, which actually solves model 1. You can also see this in the Simulink Design Optimization documentation. And then the third one is a simplex search, which is a fmin search or fmin BND, also solving model 1, because these functions, for example, cannot deal with something like nonlinear constraints.
Okay, perfect.
So here it really comes actually to be important how you model that, but the modeling actually takes place behind Simulink Design Optimization and is done for you.
Okay, before moving on to Simulink Design Optimization, let me state 2 things. You have all the toolboxes in the Formula Student license, so no need to worry, no need to purchase additional toolboxes. And the second thing is we will provide you with everything that you need to do that on your own. Models, links to the documentation, so you can actually do it at home. Well, and then as promised, the software demonstration where we are going to set up that suspension example in detail. Open the suspension model that you know from the training. That's exactly the file exchange from the training material. We will put the link to the video description, so you can do exactly the same on your PC. Let's open the model first. Well, what we see is the full suspension assembly. What I'm going to do is I will let that model run just for you to see what is actually happening. Let's scroll that a bit. So what we are doing, we are giving certain movements on these plates where the wheels are standing on, and we see how the suspension is reacting. So it's at the end, it's just sinusoidal functions acting on the chassis. And basically we see the roll center and the instantaneous centers moving. That's pretty much it. So I'm going to stop that here. What I'm going to do for you is, well, stop the simulation as well. I am going to go to the configuration parameters and switch off the Mechanics Explorer. So during this optimization, we don't want to see the animation running because maybe the model has to run 5 times. It's not required to see the model running. And now, well, what we are going to do is to go to Analysis, Response Optimization. And when it comes to optimization, well, I'm handing it over to you, Sarah. How do we set up this optimization problem?
Yeah, first of all, of course, we have to specify the design variables. This was the X and the Y that we already discussed. So here we just click on a new design variable set, and then we can choose from all the variables that we have for our model. So I choose this chassis distance that we have discussed, and I will also choose the arm length on the left-hand side.
These are all the variables that are currently in the work folder in the workspace. We just have to pick the right ones.
Exactly. Yeah. So here we have initial values given, and as discussed, we will add bounds to them. So they both have 0 lower bounds, and then what was the maximum of the
for the chassis, it's 50.
Okay.
And for the other one, it's between 0 and 100 for arm length. That's all in centimeters.
Okay. So great. Then we can press OK. And so you can see up here the design variables.
Got it.
So in addition, we have to specify the objective function.
Right.
You don't have to set up the model as we did in our slides, but you can pick from something. So here we have the tab signal bound that says specify a piecewise linear bound on a signal.
Sounds about right.
Exactly what we want to do.
Okay.
So we have to choose a signal from the model. So therefore we go back to the model.
Yeah, that's pretty easy. You just navigate to the signal. It's in the roll center subsystem, right? Then roll center height. It's the block on the bottom right. And then basically, yeah, it's exactly that signal. Afterwards, it's transformed to a physical modeling signal, but right before it's a Simulink signal, and that's exactly what we need here.
Okay. So now since I selected it, it appears here, and I can add that.
Okay.
As we discussed before, so we only are interested in this roll center height between second 5 and 55. And the amplitude is
45 millimeters. So we are interested of this height of the roll center to 45 millimeters. Perfect. Okay. I think we have specified our problem. We should save it, save that session as a file, then we can reuse it later on.
And we will call this kind of initial, right?
Perfect. Yep. Makes sense.
Okay.
So we see a certain bound. We have chosen the right signal. Now it's about setting up the algorithm.
Okay. What we have seen on the previous slide is covered in this options button here. So you have some general options that are more about showing the progress and so on. And here is the optimization options tab that we've just seen.
Well, what I would do when I start doing it, I would use the default. And let's hope the best.
Yeah. So this is what we're doing. We're using this gradient descent method. And we will use an algorithm that is predefined.
Okay.
So not for all of the methods you can choose different options. So here pattern search doesn't have different algorithms, so this is blanked out.
Yep.
But gradient descent has different algorithms.
Okay.
So you can see here there's a lot of options. For Simulink Design Optimization, the sequential quadratic programming, which is just the name of the algorithm, is the default one. And this is exactly what we want to use.
This is also the fmincon function behind.
Yeah, it's the algorithm in fmincon also said. So the method is actually the fmincon.
Got it. Okay.
And the algorithm is an option for fmincon.
Got it. Okay. Perfect.
So we click OK.
That's it. And then let's see.
we click optimize.
Yeah. Well, this will take a few minutes.
Exactly. But just for explanation, which will occur later. So this is a similar output to what we've seen in MATLAB. So it will give you the iteration number and a function count, which is called fcount, which is very important because this is, in this context, the number of simulations that you have been running.
Okay, got it.
And we will see to that later. So let's have a look at the results. So it took 2 iterations. So it started at the starting point.
Yeah.
And so you can see here that also the output says that the optimization failed to converge.
Yep.
Yeah. Another thing I want to point you to is this fcount here. So fcount means actually the number of simulations that had been run. Yeah. Okay. So we were not very successful.
Yeah.
So let's here see at the output. So this is the resulting roll center height during simulation. And this black line here is the limit that we have set.
Okay, and we are violating that.
It's still
clearly.
violated.
Yeah.
Okay, so what can we do? As we discussed, we could use a different method. We have seen that this might help. But also we could just use a different algorithm.
Okay.
Which is the one thing that we would like to try.
Okay. Well, what I suggest to do, let's load the session that we have saved, because then we have exactly the same starting point.
Exactly.
And we use a different method and algorithm for that.
Okay, great. So let's do that. So how do I do it? I
open session from file, this init one, right? And this should be it.
So, okay.
We have the same starting points. Exactly. We have exactly the same.
So if I see here, they have the same values as before, 10 and 40.
Yep.
So I will start at the same starting point. So the only thing I want to change was the optimization options. So what will we do? We will keep the method as it is.
Okay.
As a gradient descent method. And here we can change the algorithm.
Okay.
So first we took the default in Simulink Design Optimization.
Right.
Sequential quadratic programming. But we will now go to a different method, for example, the interior point method.
You say, for example, but I guess you have certain thoughts behind. Why are you picking that interior point method?
Because it's actually the default method if you start fmincon from MATLAB.
Okay.
Why is this? It's kind of the most robust method that works for most of the cases. But as I said, since this is not something we can judge in advance, since this is simulation, we will just have to try that.
Okay,
but I think it's a good thing to do.
And for us, it's good to know that it's the MATLAB default, because if you just know Simulink and Simulink Design Optimization, you see certain methods, but you don't know what is actually behind.
Exactly.
That's fine. Cool.
Okay. So here we just click OK, and then we will just restart the optimization.
Now, let's give it a try. Okay, seems that we got a result. Optimization converged.
Yeah, that's a very good sign. So
Okay.
converged means it was successful.
Yeah.
And yeah, you can see that here the last value of the signal is actually below 0.
That's
so
what we
this
wanted
means
to have.
it respects the bound. And so if you look at the signal, so the black one would be like the
Starting point?
Though it would be like the second iteration.
Okay.
And then the optimum would be like the blue signal, which is below the bound.
Which is respecting the bound. Okay.
Okay.
Perfect.
So in the last demo, you've seen that it really is important that you know how to choose different algorithms or different methods that can help you with the optimization.
Right. Well, and this brings us directly to the key takeaways. So basically what I'm going to do is I read them pretty quickly. And then we have some explanations to the key takeaways. Well, the first one is pretty obvious. You already are doing it, but keep on using optimization. Accurate modeling is really key. So in case you have information, give them to the solver. That means choosing the right methods, choosing the algorithms wisely in addition. Plus, taking the right starting point should lead you to an optimal result.
Yeah.
But this is pretty high level. So what does it mean?
So use optimization, as I already said, optimization of these kind of non-analytical function, meaning based on simulation, is challenging from a mathematical point of view, but as we've just seen, it's possible.
Right. So when I approached Sarah and talked about that model that I'm working on and I'm trying to optimize it, she said, well, do you have a function for that? I said, no, it's just simulation results. So my perspective on that is maybe it's challenging from the mathematical point of view, but I want to get the best out of it. And we have seen, or especially I have seen, that requires some additional knowledge.
Yeah.
Just clicking is probably not the right thing.
No. So model as accurate as possible is something really important. So add bounds and other restrictions on the design variables also. They might appear to be clear to you, but how should the system know that? So you always have to think that way a little bit. Then choose appropriate methods. As we've seen in the demo, it depends on how your really problem looks like. Since you don't really know, I recommend always to start with a numerical method, like if mincon, because this would be really good if it's a smooth function behind it. But also really try global methods like pattern search. They might take a little bit longer or even not, but give you additional results.
Got it.
Then choose your algorithms wisely. As in the demo, for some methods, it might not work, but others might really work. So take advantage of these possibilities that you really have.
Okay.
And starting point methods. This means if you know a solution, please give it to the solver, meaning start from that solution. There's no need to start somewhere that's really bad if you already know something good.
Sorry to interrupt, but that's a good idea. I haven't had that before. I usually know a solution because I've done a simulation run before. I have at least something that works, and why not giving that to the optimization algorithm as a starting point?
Yeah. This is one consideration, and this also means if you started that, what the optimization gives to you should not be worse than that, but even better. But also you might have to keep in mind that you still might try out different starting points, because this might be beneficial for the method.
Cool. I think this was a very heavyweight episode, so a lot of information. But at that point, really, thanks very much, Sarah, for introducing us.
Yeah, I'm glad to be here. It's really a cool application area. So
yeah. No, I think it was somehow obvious. And thanks again for joining. You're doing a lot of optimization. I felt we had to do that. And this brings us definitely to the last slide of today's episode. Let's do it pretty quick. I'm definitely interested in feedback. Also, Sarah, send us an email or go to the Facebook group with your critical feedback, with your suggestions, for example, for new topics or things that we should talk about in future. You will find all Racing Lounge videos on the webpage, like mathworks.com/Racing Lounge. There you will also find a link to the software offer. And well, if you do use our software, if you do use our tools, we would be delighted if you use our logo on your reports and on your car as well. Thanks for watching and hope to see you next time. Bye.
Bye.